The last video, we took a look at two extremely important circuits. They're the types of circuits that show up absolutely everywhere in circuit analysis, namely a voltage divider as well as what we call a current divider. However, in terms of the analysis that we ended up doing, the circuits themselves are of absolutely limited utility. And this really stems from the fact that in both the voltage divider and current divider, the number of resistors contained within the circuits that we analyzed previously was only 2. However, these concepts and some of the formulas that we developed can actually be generalized to circuits, voltage dividers and current dividers that contain a great number of resistors themselves. And that's what we actually want to cover right now. So very briefly, let's talk about the voltage divider first. Now, in a previous video, the voltage divider that we had considered looked something like this. There was a voltage source providing us with a voltage V sub S, and we had two resistors here, R1 and R2, that were hooked up to our circuit like so. So we have R1 and R2 there. We had also defined voltages V1 and V2 with this particular polarity across these resistors R1 and R2. Now, one of the things that should be pretty apparent is that the current that flows through the circuit, so suppose that there's a current I that is flowing from the positive terminal of the voltage source Vs, by virtue of the fact that these two resistors are in series with one another, one of the things that is guaranteed is that the current that flows through the circuit happens to be constant. In other words, all the resistors here are in series. And we established two things. The first is that the voltage V1 and the voltage V2 can be easily calculated using the following formulas. V1 was equal to the resistor R1 divided by R1 plus R2 times the voltage of the source Vs, and secondly, that the voltage V2 is equal to R2 divided by the sum of R1 plus R2 times Vs. Now this is what we showed, right? Now one of the things that we want to do is, again, we want to generalize this. And the way we're going to do it is we're actually going to draw our circuit, and then by taking a look at the mathematical form of the two formulas that we established previously, as well as some of the properties, we can write down an equation to calculate the voltage across any one of the arbitrary resistors that are contained within our voltage divider. So the generalization of this voltage divider looks like the following. Suppose that we have a voltage source Vs, and we have a whole bunch of resistors here, let's say R1, R2, and we have quite a number of them. Then we have another resistor down the middle. Let's say that this is R sub k. And then we end up with two last resistors hooked up to our voltage divider. Let's say that this is R sub n and this is R sub n minus 1, like this. Now, each one of these resistors, across them, there are going to be voltages that we can define. So here across R1 we have a voltage V1, across R2 we have a voltage V2, across R sub k we have a voltage V sub k, and across R sub n minus 1 and R sub n we have voltages correspondingly V sub n minus 1 and V sub n. Now, if you take a look again at the mathematical formula over here for these voltages, notice that there are certain things that should kind of stand out, right? First and foremost, the voltage V sub 1, right, is multiplied by R sub 1 divided by R1 plus R2 times V sub s, and notice that the R1 plus R2 times V sub s is shared in common with both formulas. The only thing that changes are the subscripts for the voltages as well as the resistor in the numerator. So copying the same mathematical form One of the things that we can do is we can find the voltage V sub k over here as R sub k, except now what we're going to do is we're actually going to divide by the sum of all of the resistors contained within our voltage divider formula. So here this is R1 plus R2 all the way out to R sub n, and we're still actually going to multiply by the voltage of the source that we have over here, V sub s. So in terms of the mathematical form, notice that this right here matches with the formulas that we have above, and similarly, this portion right here that I'm circling also is matching with the formulas that we have up above. Now, this formula can also be rewritten in a form that's a little bit more compact. We can say that V sub k is equal to R sub k divided by the equivalent resistance of the series sum of those resistors times V sub s, where our equivalent, again, is the series sum of all of the resistors that are contained within our network. Right? These two formulas right here are our results. And one of the things that you will see as we progress through our circuit analysis, they will become extremely useful as we move along. Thank you very much. And for the next video, we'll talk about the generalization of our current divider.